Section 2.6 is the last section of chapter 2 before we jump into chapter 3, and it's about variation and applications. I'm bringing it down a notch. You can get a little bit more complicated than what I'm doing. I'm just going to concentrate on a variation problem where they vary, directly or inversely. I'm not doing anything more than that, like combined or anything like that. So I'm going to just focus on those first two. So let's look at objective 1. It says find an equation of direct variation, inverse variation, and combined variation given values of the variables. So we're not going to worry about the combined, all right? We're just going to focus on the direct and inverse. So what's it mean direct? Like if I'm direct to you, what does that mean? Straight up, right? There's no question about what I'm asking you. I'm direct, okay? So direct variation is the same thing. As one's increasing, the other one's going to increase. As one's decreasing, the other one's going to decrease. Whatever's happening to one, it's directly affecting the other, okay? So let's look at it with an example. So it says, suppose you make $12 per hour at your part-time job. So maybe you babysit, okay? So you charge $12 per hour to babysit. How much money would you make if you worked 3 hours?
36.
How'd you get that?
I multiply 3 times 12.
Yeah, right? So that is just 3 times 12. So my 3 hours I work times my 12 hours per hour, $12 per hour, and I would get $36. What if I babysat for 6 hours? 72. And again, because I'd have my 6 hours that I worked times my $12 per hour charge, and I would charge $72. And say the parents went out all day, so I had the kids for 9.5 hours. How much would I be charging them? 114. Okay, so the whole idea is they increased. What happened to how much we made? It increased as well. Okay, so this is called vary directly. All right, so for this situation, what they want us to do is to just write a generic equation. And so this is where people say, I don't see where you can use math in real life. You do, but you don't realize you are, if that makes sense. So like, you guys would just do the math, 3 times 12, 6 times 12, whatever. But really, there's an equation that represents this, okay? So they want us to use P for the total pay and H for the hours worked. Do you guys agree that P was always kind of our answer? It's what we found, how much we were getting paid. So we're going to have P equals what? Well, what was it? Say it.
12H.
12H, right? You made $12 for every hour you worked, okay? So this is a constant, correct? And then the H varied. Is everybody okay with that? And like I said, it's just an equation that now that you have it generically, you can plug in any kind of hours that worked and you'd be able to figure out the pay for that person. All right, so what they're getting into is the definition. They make it seem way more complicated than it is. So if a situation gives rise to a linear function, f of x equals kx or y equals kx, where k is the positive constant, notice that's what we have, then we say it is direct variation, or that y varies directly with x, or y is proportionately directly related. The number of k is called the variation constant or constant of proportionality. All right, so let's write the main things. So k equals the variation constant.
Isn't this like the same thing we just did?
Yeah, so I started with a specific example, and I'm going to show you how we're going to talk about it kind of generically, but we can use kind of the same form every time we go to do a problem. So the k is the variation constant. It's kind of like your slope, your miles per gallon, your dollars per hour, whatever it may be, okay? And then y is going to always be k times x. And we usually say y varies directly. Directly as x does what? So I can't write as x ... Because we can say y varies directly as x increases, so we know our y is getting bigger. Or we can say y varies directly as x decreases, and so forth. So now it's just looking at the graph. Isn't that just a line with a y-intercept of the origin, right? mx, y equals mx plus b, right? We have the y, we have the m, we don't have the b. And notice down here, it's going straight through the origin, 0, 0. It's a positive slope. Notice our function's increasing from 0 to infinity. But notice as x increases, what's our y doing? It's increasing.
So couldn't they just be like p equals xh?
Yeah, or y equals I'd say y equals 12x is what this would be, right? Because like the outcome would be our y, the 12 is that constant, our dollars per hour that we're making, and x is the unknown variable that changes. So that's actually what I'm going to use. So I'm glad you mentioned that, Riley. I don't like when they force us to do this. I use just the generic.
I was gonna say that'd be a lot easier.
I think it is too. Yeah. And that way you don't have to remember. So again, notice as x is increasing, so is y, so the highs are with the highs, but notice also that low x's are with the low y's. They're varying directly. So go ahead and flip it over. This is how I do this problem. And guys, technically we can do it with the p's and h's that we just did on the front. I am not going to, okay? So let's read it. It says a cashier earns an hourly wage. If the cashier worked 18 hours and earned $168.30, how much will a cashier earn if she works 33 hours? So we want to point out, and most of your problems are going to say it, and this one didn't, y varies directly with x. Okay, so I'm going to write that down. How do I know? Because in general, the more you work, the more you're going to make, right? Okay, so instead of using p's and h's like they did in the front, I'm going to just put the generic formula. Y equals k times x. And what we're going to have is like those equations where we didn't know our slope b. And remember, we plugged in everything else that we could to find that one unknown b. Well, we don't know k. We don't know her hourly wage, but we know if she works for so many hours, how much she makes, okay? So we're going to use this as an ordered pair where 18 hours is our x and the 168.30 is our y, okay? So they'll always give you a specific example that you can plug in to find your k. So how much does she make? $168.30 when she works 18 hours. Okay? So they'll always give you a specific example where you have something to plug in for your x and y. Use that specific example to find your k, your variation constant. And then you can start your generic example again, but now you're going to have a k. All right? So how do I solve for k? What do I need to do to both sides?
Divide by 18.
Yep. I'm going to switch it over if that's okay. I'm going to flip it. K ends up being what?
9.35.
Yep. Okay. If you wanted to put a unit there, you can. I wouldn't worry about it because they didn't ask us specifically what K was. But that, guys, in a nutshell, is her hourly wage, right? She's making $9.35 per hour. So after you have that, come back up to your generic equation, y equals kx, but put in your k.
So it's gonna be.
Like that. Did you already do it?
Yeah.
Okay.
All I did was.
Plug in the 33.
Yeah.
Yep.
Well, I kind of just. I multiplied. Well, I divided 18 from that, and then I just did it super
Yep,
fast.
and that's what we're going to do. So, like, you get this, and that's your constant, but you know that that's how much you're making per hour. So if she worked 33 hours, what are you going to put in for x? 33 hours. So, that's, I mean, you're just doing all in one foul swoop, which is absolutely fine. Do you get 308.55? So these are probably the two things my math lab will ask you. I'll box it in. They'll ask for the variation equation. So they do want you, Riley, because you know how you kind of just used it to quickly find your answer. They might ask you to say, okay, what's the generic equation? And then with a specific example, she worked 33 hours. How much did she make? Then you plug it in. All right? So that's just direct variation. Not too horrible. So the next one is you're planning a trip to make a distance of 200 miles, but how long will it take if you're traveling at certain speeds? It's going to change, right? So the thing I want to remind us over here is distance equals rate times time. And what you're going to notice on these problems is that we have the distance and we have the rate. What we don't know is the time, right? So if I want to isolate t, what do I need to do? I need to divide by r. Do you guys agree with that? So time would just be distance divided by rate, meaning distance and rate and time and rate and distance, all those are varying proportionally, or excuse me, inversely, I should say. Okay? So if I am traveling 200 miles at 100 miles per hour, how long does it take me? 2 hours. So you're going to see something happens here. So if I'm traveling 200 miles, but I'm only going 50 miles per hour, how long is that going to take me? 4 hours. So notice it's the opposite of what happened on the front page. As our miles per hour decreases, what's happening to our time? Increasing, right? Our time's going from 2 hours to 4 hours, and then God forbid you go 20 miles per hour for 200 miles. I would not survive that trip. That would take you 10 hours. Okay. In a nutshell, I'll just let you know, I went to Butler my first semester, and it was exactly 3 hours. I was from Springfield, 3 hours, or excuse me, 200 miles, about 3 hours is what you could do, because you're going a little bit faster than the speed limit and stuff. Okay. So again, they don't mean to make it more complicated, but they kind of are.
Did you drive 3 hours every day? Or did
No,
you-
I stayed on campus. I lived there. Yeah. No. But I'm just saying, like, I knew it was 200 miles basically on the dot and about 3 hours on the dot, because you go a little bit faster than 60 or whatever. At the time, though, guys, my speed limit was only 65. Now it's 70. So you can go a little bit quicker. All right. So for this situation, write an equation relating your rate or speed to the direct time it takes. So notice the time is what we're finding, so that's going to be t. And what did we do? We had to travel 200 miles no matter what, but then what was on the bottom? Our rate. Okay? But here in a second, I'm going to write it generically. I'm like Riley. I don't like the T's and R's and P's and H's. Just give me my Y, and then my constant K is up top. But since I'm varying inversely, where's my X going now? To the bottom now. Okay, so just notice that's what it's saying down here with inverse variation. It says, if a situation gives rise to a function where f of x equals k over x or y equals k over x. Again, all the things are still the same. K is still your positive constant, but we'll say y varies inversely with x or inversely proportional to x. Meaning, as x increases, what's happening to y? It's decreasing. They're opposites. So as x increases, you notice that y is decreasing. Right? Or if you go to small x's, so as x decreases, the y is increasing, right? So the opposites are paired with each other, and that's all it is in a nutshell. So down here, again, I'm going to use this example, but I'm going to use y's and x's, all right? It says the time t, and I'm not going to worry about it, I'll say y, required to do a job varies inversely as the number of people, p, I'm going to use that as an x, who work on the job, assuming they all work the same rate. So right there, I'm not going to even read that first next sentence. I'm going to set up my equation. I know since it's inversely, it's y equals k over x. Is that okay? That's my generic. Then I know in my next sentence, it's going to give me a specific x and y to plug in, so I can find my specific k value, okay? So it says, if it takes 180 days for 12 workers to complete a job, how long will it take 15 workers? So again, we'll just focus on the 180 days and 12 workers. Remember, y was your time, so 180 will be on the left. K we don't know, and then x was the number of workers, that's 12 on the bottom there. How do you solve for k in this situation? How do you undo division? You multiply. So we're just going to multiply both sides by 12. When you multiply this by 12, the 12 up here cancels out with that. But when you multiply this by 12, what do you get for your k? It's pretty large. You get 2,160. Does that look right? So it's a big K. That's okay. I never really circle it because I feel like they rarely ask just for K. So what they're going to ask for you to do is plug K back into that generic equation of inverse proportion. Okay? So what was our generic equation? Y equals K over X, but what is our K now? 2160. So that's going to be the first thing my math lab asks you for, is just the generic equation. But then they'll go a step further and say, okay, use that equation now that you have it to solve the second part of the problem. So if you continue in that sentence, it says, if it takes 180 days for 12 workers to complete a job, how long will it take for 15 workers to complete that same job? And so now, look, they gave me a new X value to plug in.
You just divide that by
You got it. When you do that, you get 144 days. And do you guys agree, as your workers increase, the time it takes to finish the job should go down? Because more workers, they're being able to complete more work. So they inversely are related.